Welcome to Astronomy 103. We're picking up with what happens to stars once they leave the main sequence. Okay, so we're talking about stellar evolution. So what we're going to do is we're going to talk about stellar evolution. We're going to look at the stages, and we're also going to look at what's going on the HR diagram, because that's usually how we identify things. In particular, we're going to match up some of those classes of objects we talked about to what sits on the HR diagram and where. So evolution? Now, normally when you hear the term, you think of biological evolution. You think of Darwin and natural selection, all that stuff. But the word evolution just means a change with time. So Darwin was interested with how species and life changed with time. We're interested with how stars change with time. So stellar evolution is how a star changes as time passes. So we've talked about formation, and we've talked about that what happens is a star ends up on the main sequence and it stays there burning hydrogen to helium, but eventually it runs out. All of its core is filled with helium. It can no longer fuse hydrogen into helium. The other important thing is that the rest of the star outside the core is in an equilibrium. It's balanced. Gravity is trying to push everything in, but the thermal pressure, the hot gas that's constantly colliding with itself, is pushing back. It's inflating it. So for a main sequence star, this is pretty much balanced because the core is keeping everything nice and hot, preventing gravity from pulling everything in. But now we're going to run out of fuel in the core. The fusion's going to stop in the core. So what happens is the star starts contracting. We've run out of energy going out, so now the gravity is starting to win and push everything in. Now this heats up the core, and it heats up the layer right outside the core, which then starts to fuse. It was just barely below fusion temperatures, and now it's above it. Now we call this layer the hydrogen shell, because it's a shell of hydrogen around the core, like an M&M. So the inner parts of the star are now getting hotter, and they're pushing outward. And since the shell is a bit bigger than the core, there's more energy going in, and the outer layers of the star started puffing up. They cool off as they puff up. So what happens is the star overall swells up, and the top layers also cool off, which might seem a little weird since the core is getting hotter. But because the star is bigger, as the gas expands out, it cools. So even though the core is hotter, the outer layers are much cooler, and the star is generally bigger. So you can have more of a difference from core to surface. So the first thing that happens is the sun becomes what's called a subgiant. It's slightly swollen. It's slightly cooler than it was. Let's see where it is on this little excerpt of the HR diagram. But as it makes more and more helium, its core is getting bigger. The layer of fusion is expanding outward, and you're pushing more and more on the core. The core is putting out more and more. The core is getting hotter. The shell is getting bigger. The star becomes a red giant, and it gets much, much, much more swollen. It can be 100 times bigger than it was, or several hundred times bigger than it was as a main sequence star. And because it's so big, again, the surface is really cool, even as the core is hotter than it was as a main sequence star. So it's large, it's bright, and it has a relatively cool photosphere top layer. So this is kind of a schematic of what's going on with a star like our sun. You can see, cut off the edge of star birth. So you can see the sun stays mostly pretty much the same kind of size for billions of years, swells up a bit as a subgiant, and then as a red giant, it gets huge. So what a red giant is, it's far larger than a main sequence star in terms of radius. It's not too dissimilar in mass. And because it's swelled up, even though it's putting out a lot more energy from its core, or rather its surface is very cool for a star. It's much more likely to go from a G-type to a K-type or an M-type star. Now its core is inert. Its core is full of helium. It's very hot, but not quite hot enough to get fusion going. Now, the layers that just outside the core are still hydrogen, and they're hot enough to fuse. So you're making more helium. You're building up this core, helium core. Remember, we call that the shell. So as we pile more helium onto the core, it keeps getting hotter. Now, this is kind of a cool graph I found. It's the change in the sun's brightness, the luminosity of the sun with time. So you can see there's a very spike early on as the protostar kind of settles out in the main sequence. When the sun's on the main sequence, its brightness changes a little bit. Again, stars in the main sequence mostly do the same thing, but they're not completely immune to change. And the sun leaves the main sequence at about 10, 11 billion years from its formation. Then it goes through its subgiant phase and its red giant phase, and it's constantly getting brighter. As the core gets hotter, we're getting more and more fusion in the shell. We're getting more and more energy going out through the star. And eventually what happens is the red giant's core gets hot enough that helium fusion starts, and it starts all at once. The core is under a condition where as soon as helium fusion starts, it spreads throughout the core. That's why we call it a helium flash, because it happens in a flash. And especially in star terms, stars, you can kind of see the units on this graph, it's billions of years. So a flash in a billion years is not necessarily a flash as we see in the sky. And the star stabilizes. It's now fusing stuff in its core. It can settle back into an equilibrium. So this fusion process is called helium fusion. Now the trick with helium is for such a small molecule, it's really stable. It has the average helium nucleus has 2 protons and 2 neutrons. If you try to stick 2 together, they don't want to stick. They'd rather be 2 heliums than 1 beryllium-8. So what you have to do to make helium fuse, you take 2 heliums, you stick them together, and then you add a third one really quickly before they break apart to get a carbon-12. Now you can see this on this graph. So this graph is, we've got atomic mass on the bottom, we've got mass per nuclear particle on the top. If you can go down, that means you're getting energy out. You're able to power your star by that. So hydrogen to helium, you release energy doing that. Your 4 hydrogens weighs less than 1 helium. So some of that mass becomes energy and we power the star. The next thing that has less mass than the equivalent number of helium nuclei is carbon. 3 heliums have less mass than 1 carbon, so we can do that. We can't do it with anything intermediate, which is why it's hard to do. And you notice the gap in the graph is much less. You're getting much less energy per proton or neutron in this molecule. So this isn't getting us as much energy per fusion event. And the fusion is also happening much faster because, again, we've just crammed all this helium into the core of a star. It's really hot and really dense. So, but again, we're settled out into something that's relatively stable. Now, we have core fusion, which means that the star can kind of settle out. Now, it's still very, very hot right outside the core, so we're still getting that hydrogen shell is still going. So it's not quite as stable as a main sequence star. And in particular, one of the things these kinds of stars do is they pulsate. Their surface kind of moves in and out over periods of days or weeks, like they're breathing. We're going to talk more about that later. So what happens is they're stable. They're more stable than they were as red giants. So they move back towards the main sequence. They don't get there, but they kind of sit they shrink back down. Their surfaces get hotter. And we call this region on an HR diagram the horizontal branch because it looks kind of like a horizontal branch coming off the big direction of red giants, big stream of red giants on the HR diagram. And exactly where they sit on the horizontal branch depends a lot on what happened as a red giant. Because red giants are so swollen, they tend to lose a lot of mass from their outer layers. So we stop being able to predict as reliably what happens with a star because it depends a lot on that mass loss. All right, so We have our star nicely fusing helium in its core to carbon. It's making a little bit of oxygen and neon on the side, and it's eventually going to run out. So again, we repeat this process. The core runs out, you get contraction of the inner parts of the star because you're no longer putting out the energy to balance the gravity. The shell around the core ignites, so you get a second shell. You still have the shell that's turning hydrogen to helium, but now you have a shell of helium burning to carbon. And then you still have your carbon oxygen core that's heating up. Now, again, just like whenever we get shell fusion, we get a lot of energy coming from the inside of the star that is not particularly stable, so the star starts swelling up again. So the star goes back to being a red giant. So this is, again, what it's doing on our HR diagram. It becomes a subgiant, becomes a red giant. It goes back down a bit as it starts fusing helium, not all the way to the main sequence, but closer to it. Runs out of helium, it becomes a red giant again. And sometimes astronomers call these stars AGB stars, asymptotic giant branch stars. And again, this is basically named by the pattern they make on the main sequence. They're all the way at the top of where all the red giants are. Now they can get even brighter than the second time or the first time because now they have two shells and their core is even hotter. It's heated up past the temperature where you start fusing helium. Now somewhere around the 8 to 10 solar masses, that's the original mass of the star. Somewhere around those kind of stars, 8 to 10 solar masses, we hit a limit. Stars below those masses can't get their cores hot enough to fuse carbon. So no matter how much they contract their core, no matter how much the weight of the star bears down on that core, it's never going to get hot enough to start fusing again. It's stuck. And some stars don't even reach this. Really tiny stars below about a quarter of a solar mass can't even get to the carbon stage. They have to stop at helium. On the other hand, those stars haven't run out of fuel yet, so we don't talk that much about them. They're interesting to astrophysicists to consider what'll happen, but we don't have any real examples. So we mostly deal with the sun-like stars up to about 10 solar masses that get to carbon and then get stuck. So this is kind of our stage. We have our sun. This is the path of what our sun will do in the future in 4 to 6 billion years. It'll become a subgiant as it runs out of hydrogen in its core, and then a red giant. The core is shrinking and getting hotter. The outer layers are puffing up and getting cooler. Eventually, the core hits that helium flashpoint. Helium starts fusing into carbon with a little bit of oxygen and neon, or the future sun can start to contract, get the outer layers under control. They heat up again. The star gets smaller, so it's slightly less luminous, and the core is more stably fusing. Runs out of helium. It does the process again. It gets that shell fusion going. So it's got two layers of fusion, one of hydrogen, one of helium. Again, the core is still contracting, trying to find some more energy to keep the star from totally contracting, but it can't. It can't get that carbon at the center hot enough, so it's stuck. So it's constantly contracting the core, and the energy from the shells around the core is pushing the outer layers of the star out further and further. And eventually what happens is those layers just detach. They reach escape speed and they're gone. They just are going to swell out to infinity driven by the star's light. And when they're close enough to the star, they're detached, but they're close enough to the star within like a light year, the really hot core can keep them glowing as a nebula, a cloud. Now, rather than being the star-forming nebulas we talked about earlier, we call these planetary nebulas. Their original name was because a lot of them look like kind of faint, ghostly gas giants through a small telescope. So they don't really have much to do with planets, and they're very distinct from protoplanetary nebulas. These are really short-lived for space stuff. They're only around for about 10,000 years, but they're often some of the prettiest things to look at in the sky, and they're especially nice if you have a small telescope because they tend to be pretty compact and easy to see, even in like Lincoln. So here are some pictures. The Helix Nebula kind of shows, you can kind of imagine if you didn't have a very good view of it, that it would look a bit like a spherical bubble, like a planet. But a lot of them, like the Butterfly Nebula below, they aren't as nicely spherical. You get this kind of two-lobed shape, butterfly. This is what stars of modest size do. Anything below, again, 8 to 10 solar masses. When they die, they go through a few phases of red giant, and then they form a planetary nebula, and then what happens next we'll talk about in the next lecture. But, you know, most stars are below about 10 solar masses. So most stars are below about 10 solar masses. So this covers most of the stars that have died, but not all. So now we need to look at the massive stars. This might look like the plot I showed in the previous lecture, where I was telling you stars collapsing onto the main sequence. But this is the reverse. This is stars leaving the main sequence. So all the bottom ones, from about half a solar mass to 5 solar masses, that's showing them ascending the red giant branch. That's showing how they could go from being main sequence stars to red giants and kicking off helium fusion. You can also see some of the time scales. Massive stars, they can't really get that much more luminous without blasting themselves apart. So when they run out of helium, they swell up again because they're contracting their core. They've got that hydrogen shell thing, just like less massive stars. But they don't gain that much luminosity. A red supergiant isn't that much brighter than the blue main sequence star it used to be. So the basic process until carbon is the same. You fuse the element, you run out, you contract the core, you create a little shell around it until eventually you kick on the next element. Massive stars can keep going though. A few in the kind of transition range between 8 to 10 solar masses can go maybe one more step. They can fuse the carbon and oxygen into magnesium and neon. But let's talk about the much heavier ones, like that 15 solar mass one on this plot. They can keep going. They can go from carbon and oxygen, magnesium and neon, silicon and sulfur, until they get to iron and nickel. So let's go back to that plot I showed you. Again, we have atomic mass at the bottom and mass per nuclear particle at the top. So this is saying that 4 hydrogens has more mass than 1 helium. That's why we can fuse them to get energy. That mass becomes energy. E equals mc squared. 3 heliums is equal in number of nuclear particles, number of protons and neutrons to 1 carbon. And again, you can fuse that. You can fuse 3 heliums to 1 carbon. And you can see if you add a helium and a carbon, you can get oxygen plus energy. And you keep going, but each of these is a diminishing returns. You're getting less and less energy per reaction. And eventually what happens is you get to iron 56, an iron with 56 protons and neutrons together, and you get stuck because that is the minimum amount of mass per particle you can get. If you try to fuse iron and to make it heavier, it takes energy. If you try to break the iron back apart to get those light elements back, it takes energy. Iron is the stopping point. No matter how hot and how dense you make the star, it cannot get energy out of iron. It cannot get blood from the stone. So now this is where massive stars stop. Is less massive stars stop because they are not mass enough to go on. They don't have enough gravity to squish that core. The biggest stars stop because basically the laws of physics say you can no longer get energy out of your core, at least not by fusion. And so let's talk a little bit about star clusters before we end the lecture. Because a lot of the way we can test our theories about how stars age and die is by looking at a bunch of stars we know to be about the same age and seeing what they're doing. Because remember, stars form in clusters, so all of those stars are roughly about the same age, but they all have different masses. So we can use our models of stellar evolution to make a prediction about what we would see on an HR diagram, and then test it by looking at a cluster. And not only will we learn how old the cluster is, but we'll be able to make sure we can match that cluster to a group of stars of different masses but the same age. So for instance, here on the left, we have our theory. This is what a cluster that's 3 million years old would look like, or a cluster made of 3 million-year old stars. And you can see out to maybe about 10,000 Kelvin, all those stars have settled onto the main sequence. Farther out, they're still forming. They're still contracting, they're still protostars. So if we compare it to observations, this is an HR diagram from the cluster NGC 2264. And you can see they're kind of similar in that the stars brighter than about 100 solar luminosities are on the main sequence, and the stars fainter are not quite yet. Now, it's not as nice as the theory because in reality, these stars are forming at slightly different times. So they're all slightly different ages. So the kind of average age would be about 3 million years, but there'd be some variation of maybe a few million years on either side. Incidentally, here's a picture of this cluster. It's called the Christmas tree cluster. You kind of see why it's called that by looking at the bottom. And we know this must be a young cluster because it's still surrounded by a lot of the gas that formed it, which makes sense because a lot of the stars haven't settled out, only the most massive have. Now we call these clusters open clusters, and I've mentioned them before. These are young clusters that formed out of a big star forming region, and they're still kind of attached to each other gravitationally. So let's look at an older cluster. This is M41, and this is its HR diagram. You can see the stars from about 1 to 10 solar luminosities are sitting on the main sequence, but they're starting to branch off at around maybe 10 or 20 and leave the main sequence. Those stars are starting to form red giants and red supergiants, and you can see a few red giants off at the upper right. And you can even see it in the picture that a few of the stars, if we go back to the Christmas tree cluster, most of these stars are nice and blue. But in M41, not only is there no more gas, these stars have already formed, the star forming has shut off for a long time, but also some of the stars are starting to be red. Some of the brightest stars in this cluster are the red giants. So this is an older open cluster. It's about 200 million years old. But there's a second kind of cluster. We're going to talk more about these as we get to galaxies. These are globular clusters. Unlike open clusters, which kind of live in the plane of the galaxy with lots of other stars around them, globulars, like the one in my background, are in otherwise pretty clear portions of our galaxy, and many of them are really old, older than our sun. They're some of the oldest things we have in our galaxy. And we know that because we plot their HR diagrams. So this is a picture of 47 Tucanae. It's the second brightest globular cluster in our sky. Unfortunately, it's a southern hemisphere object. And it's 13 billion with a B years old. When we look at its HR diagram, you can see stars that we don't have the main sequence on here, but stars that are a bit under the mass of our sun are starting to leave the main sequence. And you can see there's a whole lot of red giants, and that all the bright stars we see are red giants. Also kind of see the horizontal branch there, and why we call it that. That little kind of spur off the big line of stars is the horizontal branch. That's where helium-fusing stars live. So in summary, sun-like stars, they end their main sequence life. They become red giants. They then get hot enough that their cores can start to fuse helium, so they become helium-fusing stars, horizontal branch stars, you sometimes hear them called. They'll return to being red giants when the helium runs out, and their final stage is going to be their core keeps contracting and their outer layers get shed in a planetary nebula, and which will eventually dissipate and return to just the normal gas in space. And we track that on the HR diagram. We see the sun-like stars move to the upper left or upper right, move back towards the main sequence, and then move back up the upper right. High mass stars can fuse everything up to iron. So when they leave the main sequence, they just track straight straight to the right. They don't increase much in luminosity. And they might wiggle back and forth as they go through their fusing things up to iron, or they might not. And so these are supergiants. So next time, okay, let's keep going. What now? What's after a planetary nebula? What's after a high mass star fills its core full of iron that it can't fuse? And that concludes white dwarfs, supernovae, and black holes. All right, see you next time.